So the next step in when finding our when solving for our stresses, we need to find our neutral axes. Okay, so our neutral axis occurs when the bending stress is equal to 0. So when sigma x is equal to 0 for a given cross section. Okay, so the reason we're interested in finding the neutral axis is that the points that are furthest from our neutral axis undergo our maximum and minimum bending stresses, and that's where the points where we'd be interested in designing our cross section to be able to withstand the given applied loads. So for the neutral axis, we're going to find our neutral axis, we're going to set our stress along the x-axis equal to 0. So we take this equation from earlier in the lecture, right, and then we're going to solve for the we're going to rearrange this equation and solve for the ratio of n over m. Okay, so that ratio of n over m we can think of as being an angle, which that angle we'll define as our angle alpha. Okay, and that angle will have, so we can think of our neutral axis as occurring along a line. Alright, and then that angle alpha will have a component along the m-axis, and it'll have a component along the n-axis. Okay, so to determine what that angle is, we can know that the ratio of n over m would be a tangent function. Okay, and we're going to define the tangent of angle alpha would have to be equal to the ratio of the moments being applied to the system about the n and m axis, as well as the moment of inertias about the m and the n axes. Okay, so an alternate way to find the location of the neutral axis is you can define an angle beta, which would be from the original YZ coordinate system. Okay, so that angle beta will go from the y-axis to, sorry about that, we'll go from the y-axis to our neutral axis. Okay, um, so we can define that angle beta would be equal to tangent alpha plus theta p, which we can write in terms of our moments about the y and z axes using this formula. Okay, so, and in a similar fashion, we can solve directly for the stresses at any point using by plugging in the values for m and for the moment about the m-axis, the moment about the n-axis, and then the moments of inertia is about the m and n axes, as well as the coordinates m and n. We can plug those in terms of x, y, and in terms of y and z, and we will get this following equation here. So you can use either method to solve for the stresses or or for the location of the neutral axes. It's whatever is easiest for you to calculate or to use for the given problem.